Hello, welcome to tutorial 5. In this tutorial, I will discuss two different topics. So the first topic is mesh analysis, and the second topic is Thevenin equivalent. So let's get started with the mesh analysis. Mesh analysis is really similar to nodal analysis. However, in mesh analysis, we are uh, interested in finding the minimum number of circuit currents. This is in contrast to node analysis. In nodal analysis, we were interested in finding the minimum number of voltage node. Okay, but here we are interested in the circuit currents that could represent the voltage and the current of different elements. So how can we do mesh analysis to a given circuit? So mesh analysis is a three-step process. So we have a step 1, step 2, step 1, step 2, and step 3. So also similar to node analysis, we have to identify here the minimum number. Of meshes. In node analysis, we were interested in finding the minimum number of nodes, not a mesh. Here we are interested in finding the minimum number of meshes, and mesh is we mean really by mesh is a loop. So we call this thing is a mesh or a loop. Okay. So if you remember, in node analysis, we were interested in finding the minimum number of nodes. So here in node analysis, we were interested in finding the minimum number of nodes. So this is a node, and while this is a mesh. Okay, so this is the main difference between node analysis and mesh analysis. Also, a second difference is in node analysis, we were interested in finding the location of the ground. Here, we don't really need any ground or reference signal for our calculation. So we just cancel out the step of finding or locating the ground. Okay. The first step here is to identify the minimum number of meshes. How can we identify the minimum number of meshes or reduces the number of meshes? We have two cases, case A and case B. So when there is a current source between two meshes, we have to combine the two meshes into one big mesh, and we call this mesh is a super mesh, like in this case. So in this case, we have a current source, and this current source is common between two meshes. So I will combine these two meshes or two loops in one big loop. Okay, and we will learn how to relate the current of the first mesh I1 to the current of the second mesh I2 shortly. We will learn how to relate them shortly. But the main thing is in order to reduce the number of meshes, whenever we see a current source common between two loops, we will extend the loop or combine these two loops. Okay, in order to reduce the total number of meshes. Okay, so this is the first case. When there is a current source common between two meshes. The second case is like when there is a current source, but this current source is not common. It's not common between meshes, or we call it individual like current source. An example for this one is something like this. We have two loops, or two mesh. This is mesh 1 and this is mesh 2, and we have here a current source, and this current source is mainly related to loop 1. Okay, so this is a different case. In this case, we will reduce the number of unknowns, because we will say directly that I1 is equal to 5 amperes. So here in this case we'll say, yeah, as long as I1 in the same direction, so this is I1, so I1 is clockwise, looping clockwise, so in that branch I1 is going up, so we'll say that I1 is equal to 5 amperes directly. So right now we reduced the number of unknowns by 1. Initially we had two unknowns, I1 and I2, but by identifying that this current source is looping inside I1, so we reduced the number of unknowns by 1. Okay, so let's consider the second case, which is when we have a current source and this current source is common between two loops. We said like, okay, we will use combine the two meshes into one mesh, and we will say this mesh is super mesh, and we call this one is super mesh. Okay, how can we relate I1 to I2? We can relate I1 to I2 by doing KCL around, let's say, node P. So KCL around node P, we have I1 here. I1 is flowing and like clockwise, so that means like in that branch this is the direction of I1, and also in I2, so I2 is also following clockwise, so it means like this is the direction of I2. So doing KCL around node P, KCL around P, flow in is equal to flow out, so we have I2 flow in, flow out, we have 5 plus I1. So this is how to relate the current of two loops or two meshes with a super mesh. Okay, so in these cases, in these two cases, we reduce the number of unknowns by 1. Here, instead of having two meshes, we have only one mesh, and we have an extra equation given by this equation. Okay, so right now we are done from step 1. We are already identified the minimum number of meshes. What should we do? The second step is to do KVL around each mesh to get one equation for one mesh. Okay, so suppose we have three different meshes. I will do KCL around this mesh, so in order to get 3 different equations. I will be able to solve the third step is solving these steps, this equation simultaneously. I will be, in order to find I1 and I2 or whatever the number of unknowns, I will be able to solve it when the number of unknowns, number of i's, is equal to the number of equations. And that's what I'm looking for, is to find or to construct, if I have 3 unknowns or 3 meshes, I have to construct 3 different equations. Okay, so by solving the 3 different equations simultaneously, I will be able to find I1, the I2, I3, or whatever the number of unknowns that you have. So let's start with example 1. In example 1, we are interested in finding VO, the voltage across these two terminals. Let's say like this is A and this is B. We need to find VO. Okay, so using mesh analysis. So in order to use mesh analysis, we have to identify the minimum number of meshes. Here we have 1, 2, 3. So mesh, it means a loop. So we have 3 mesh. This is not a mesh because it is not a closed loop. It is not a closed loop. This is an open loop. So we have three closed loops. So I will identify three different currents. So let's say this is I1, let's say this is I2, and let's say this is I3. Okay, so we identified here three meshes. So the first step is to reduce this number of three number of meshes using the two tricks here. So the first trick, it says like search for a current source that is common between two nodes. Here we have two current sources, but these current sources are not common between meshes. So here this one is not common and this one is not common, so I will not be able to use this one, A. So what about P? It says like search for the current sources that are individual. Yeah, we have here one current source, and this current source is individual, like is related only to loop 1 or mesh 1, and also this current source is related only to to loop 2. So what should I do? Yeah, I will reduce the number of unknowns by saying that the current here is equal to the current there. Okay, so how can I do it? In order to do it correctly without messing up, let's say we do KCL around P. Do KCL. This is like the systematic way in order to find the current of this one, because I have seen in many exams like people saying like finding I1 not wrongly. So I'm trying to give you like a systematic way to find I1. So I will do KCL around P. So in KCL around P we have here I1 is clockwise. So it means like I1 is going in to P. So this is I1, and the current is going 2 amperes is 2 milliamperes is going also in is going into P. So we have flow in is equal to flow out. So flow out is 0, flow in is 2 milliamperes plus I1. That's give us I1 is equal, this give us is equal to minus 2 milliamperes. Okay. What about what about I2? So in order to we will be able to find I2 directly. However, I really prefer to do KCL around, let's say, Q. So Q, KCL. So we have also I2 is going clockwise. So it means like I2 is going into the node, and the 4 milliamperes is going out. So we'll say like flow in I2 is equal to flow out, so 4 milliamperes. So right now we reduced the total number of unknowns, which is 3, because the total number of meshes is 3. We reduced them into one mesh, or to one equation. So I need to find one equation, and this equation is function in I3 in order to find I3. Okay, so let's do KCL. So the second step, so after identifying the minimum number of meshes by reducing by following these two steps, I have to do KVL around the rest of the meshes. So we have only one mesh here that has unknown, which is I3. So I will do KVL, step 3, KVL around loop or mesh 3. Okay, so in order to do KVL around mesh 3, we have here 4, because the current here I3 is going in, so we'll assume it's going in from a positive node. So we have here 4 I3, and the current here is I3 is going in, but I1 is going out. Like how to, let's say like this is the direction of I, this is the direction of I3. however the direction of I1 is in the reverse direction. So I have to say that the current here in the 4 kilo ohms is given by I3 minus I1. So I3 minus I1. Okay. What about the voltage across the 2 kilo ohms? So we're assuming that I3 is going in from a positive terminal. So we'll have 2, and the current here in this branch is I3. So I3 is going in that direction, however I2 is going in the reverse direction. So we'll have I3 minus I2. And by the way, this is always the case because we are assuming here that all the current have the same direction, clockwise direction. So as long as you're assuming the same direction of the current, like all of them are going clockwise, so the common branches, in the common branches we will have like I something minus I something. Which we will start by the current of the loop that we are studying minus the current of the other loop. So if we are studying this branch, we'll say I3 minus I1. If we are studying that branch, we'll say I3 minus I2, and so on. So let's continue our KVL. So here in this this part we have this branch. There is no current in that loop, so it means like the current here in this branch is only I3. So we'll have here plus minus I3, so it's plus 6 I3, and we end up that we end up with like here the current is going from a negative terminal, so it means minus 3 volt is equal to 0. So we have equation, and this equation, this is IC. So in this equation we already know I1, we already know I2, so the only missing thing is I3. So single equation in single unknown, so I will be able to find I3, which is equal to I3 will equal to 0.25 milliamperes. Okay, however, this is not the final answer. We are interested in finding VO. So in order to find VO, as long as you are asked to find a voltage, so most probably you have to use KVL. So in order to find VO, I have to do KVL around this loop. I have to do KVL around this loop. Okay, so doing KVL around, let's say, loop 4. KVL around loop 4. We will have here the current. The current is going from going into A from a positive terminal, so we have V1, VO, and also going here from a positive terminal, so we'll have plus 3 volt. And here we assuming that the current here is going I3 is going here downward, so it means like the current of this loop, is going into from a negative terminal, so it will be minus it will be minus I3 multiplied by 6, which is equal to 0. So we end up with VO is equal to I3 multiplied by 6 minus 3 volt, which is equivalent to 1 this gives us minus 1.5 volts. So this is VO. Okay. So let's consider the second example. In the second example, we are asked to find I/O using mesh analysis. Using mesh analysis. So we have here also, as long as we are required to find something using mesh analysis, we have to identify the meshes. So here we have 1, 2, 3 meshes. So we have like mesh 1, we say the current here is I1, the current here is I2, the current here is I3. Okay, so after identifying the number of meshes, we need to reduce this unknown from three meshes to 2 or 1 or whatever. Okay, so we have to follow the first step. The first step says we have to search for a current source which is common between 2 meshes. So is there any current source? Here we have only one current source, and this current source is common between 2 meshes. Yeah, so I will be able to reduce the number of unknowns from 3 to 2. Okay, so I will according to 1A, I will be able to combine these 2 meshes together because that this current source is common between mesh 1 and mesh 3. Okay, and also here we have something really interesting here, that we know that the current of that branch is IO. So as long as the current of that branch is IO, I will be able to relate IO with I2. How can we do it? We can do KCL around node P. Okay, so using these two tricks, I will be able to reduce the number of unknowns. Initially, we had how many unknowns? We had I1, I2, I3, and IO. We had 4 different number of unknowns. This is because of the 3 meshes, and this is the given unknown from the very beginning. So I need 4 different equations. By doing these 2 tricks, I will be able to reduce the number of unknowns from the number of equations from 4 to 2. Okay, so let's do it. So I will start with this one. So with this one, we know that whenever we have a super mesh, this is a super mesh because we combine 2 meshes into 1 mesh. It's similar to the super node when we combine 2 nodes into 1 super node. And by the way, in nodal analysis, we combine nodes when there is a common voltage source between them. And here we combine super meshes when we have a common current source between them. So there is an analogy between mesh analysis and nodal analysis. In mesh analysis, we do KVL. In nodal analysis, we do KCL around nodes. Okay, so this is the main catch to get by this analogy if you forget something in the exam, because I have seen so many students they combine post method or in one in solving one equation, one problem. Okay, so let's get back to our main topic. So we have here a super mesh. In this super mesh, we are interested in relating. We have, whenever you have a mesh, you have to relate the current of these meshes together. So we need to relate I1 to I3. In order to relate I1 to I3, we have to do a KCL around certain node. So I will pick this node, let's node Q. I will do KCL around Q. I'm using this stupid technique just because make it systematic in order to prevent you from doing mistakes in the exams. Okay, so here we have I1 is going out of the node because it's clockwise, and also we know that I3 is going into the node, so flow in is equal to flow out. So flow in is I3 is equal to 3IO, flow out 3IO plus I1, and this is equation 1. Okay, so this is the first equation. Okay, the second equation that I have to do is to do KVL around this super node. So you have to do KVL around this big super node. So let's do KVL around this big super node. We have here the current of the super node. We have here I1 in this super node. I1 here is going in from a negative terminal, so we'll write minus 35, and I1 is going here plus negative, so we'll have plus 10 I1 minus I2. So this is the second equation, and so this is the second equation, and here we have here 2 ohms, this 2 ohms, these 2 ohms, and these 2 ohms, it has I3 minus I2, the current is inside it, so it has 2 I3 minus I2. And lastly we have here this resistance, which it has 8 multiplied by I3, so plus 8 multiplied by R3, and all this is equal to 0. Okay, so this is the equation, so we can reduce this equation to 10 I1 minus 12 I2 plus 10 I3, which is equal to 35. Okay, so this is the second equation. Till now we did not benefit from the knowledge here that I1 here is the current of that branch. In order to get benefit from this one, we have to do KCL around node P. So I will do KCL P. That's mainly because I know that the current in certain branch, whenever you know the current of certain branch like this, you will be able to relate the current of this branch to the current of the loop itself. It is really similar to the second node here, because here we know that the current of this branch was 5 ampere, so we related this 5 ampere to I1. We'll do the same thing here. We relate IO to I2 by doing KCL around P. So I2 is going into node P, so flow in, and IO is going out, so IO. So I2 is equal to IO. So this is the third equation, and this was the second equation. And by the way, this node, this equation reduced the number of equations from 4 to 3, because I already know that IO is equal I2, so I can substitute with this one into 1, and also into 1 only. Okay, so where I can get the last equation, so because I have 4 unknowns, so I need 4 different equations. So I have to do KVL, I'm sorry, KVL around mesh 2. So doing KVL around mesh 2, we'll have 4, we'll have here 4, the current in this resistance is only I2, so we'll have here 4 I2, and the current here is also 10 multiplied by I2 minus the current here is minus I1, and lastly the 2 ohms resistance, I will have 2 multiplied by I2 minus I3, which is equal to 0. So this is last equation, and we can reduce this equation to 16I2 minus 10I1 minus 2I3 is equal to 0. So this is the fourth equation. So we have here equation 1, equation 2, equation 3, equation 4. So I know that your calculator can only solve 3 different equations. So this is not an equation. This is just an equation to reduce the number of unknowns. So instead of using IO here in 1, I will use I2. So by substituting here with 3, sub 3 into 1, you will get only 3 equation in 3 unknowns. Okay, so 3 equations, 3 unknowns, so we will be able to solve it. So I will write the solution, the final solution here. Sorry for that. So I1 is equal to 0.8413 amperes. I2 is equal to 1.0096 amperes, and I3 is equal to 3.87 amperes. Okay, so this is the final answer. Okay, so the last example here that we have for this question, we have this circuit, and this circuit contains I forgot to write find IO. This equation contains this circuit contains 4 different meshes, and we already given I1, I2, I3, I4. So we have here so already the number of meshes are identified, so we need to reduce this number of meshes. So we have to search for step 1, search for a current source that is common between 2 meshes. So let's identify this one. So we have here how many current source. We have 1 current source and the second current source. So if this one is common between 2 meshes, yeah. So this one is common between mesh 1 and mesh 2, and also this one is common between mesh 2 and 3. So here we have 2 common. So because this one is common between mesh 1 and mesh 2, so I have to combine mesh 1 with mesh 2, and also because this one is common between 2 and 3, so I have to combine 2 with 3. So I will continue combining 2 with 3, so we'll have a very big mesh which is super mesh. So here we have super mesh, and this super mesh will give me, because it contains three different meshes, so it means like I need to use to find three different equation using this mesh. The first equation is by doing KVL around the super mesh. The second equation is by relating mesh 1 and mesh 2 currents, and the third equation is to relate mesh 2 and mesh 3 currents. And it's really important to write it down like this in order to not get lost in the exam, because eventually you will have so many unknowns. Okay, so this is the first thing. Do I have any? This is the first step. The second step is to identify if I have like a current source that is individual current source. No, we don't have individual current sources here, so we have to continue like that, okay, with this. And the last step, we will do KVL around loop 4 or mesh 4. Okay, so let's start with the easy thing first. Step 1 is KVL around the super mesh. So doing KVL around the super mesh, we have here 2 KVL around super mesh. So we'll have 2 I1, and we'll have plus 6, this one is 6 I2, 6 I2, plus here this one. I'm trying to pick the one that doesn't contain common currencies. So this one is 4 I3, so it's 4 I3, and the last one here in this loop is this one, which is 8, and it has two common currents, I4 and I3. So I will write it plus 8 I3 minus I4, and all that thing is equal to 0. So this is the first equation. The second equation I have is I have to relate the current of mesh 1. I have to relate the current of mesh 1 I1 to the current of the mesh 2 or related to I2. So in order to do that, I have to find a node in order to do KCL around it. So in order to do that, can I choose this one? Can I choose this node? No, because this node is common here, I1 5, and this 3 IO, and the current here. So I should choose this node. Let's name it node P. So KCL around P, I have flow in is equal to flow out. So flow out is I1 plus 5, which is equal to flow in I2. So this is the second equation, equation 2, and this is equation 1. So in order to find the third equation, I have to relate the current. I have to relate the current of mesh 2 with the current of mesh 3. So I have to do KCL around certain node. Definitely, this is not a good node because it contains so many currents, 4 branches of four current branches. So definitely this is the good node. So let's this node Q. So doing KCL around Q. So flow in is equal to flow out. So flow in. So we have here flow in is equal to flow out. So flow in is 3 IO. Flow in is 3 IO, and also here I3 is flow in, so plus I3. Flow out is I2, so it's equal to I2. and this is equation 3. Okay, so we need to find equation 4, because how many unknowns that we have? We have I1, we have I2, we have I3, we have I4, and we have IO. So we have here 5 unknowns, so we need to find 5 equations. Okay, so the fourth step, the only mesh that we did not do KVL around it is mesh 4, so we have to do KVL around mesh 4. So doing KVL around mesh 4, we have 8 here multiplied by I4 minus the current of the other loop, which is I3, plus the current here is I4 multiplied by 2, so 4 multiplied by I4, 2 multiplied by I4, and the last thing, that the current here is going in from a positive terminal, so it will be plus V equal plus 10 is equal to 0. Okay, so this is equation 4. So we need to find the fifth equation. So the fifth equation, I need to relate one of these things to IO. So in order to do that, I have IO is common here, so this is IO and also this is IO. So for this IO, I already use it in relating mesh 2 with mesh 3, so I already used this one. So the only missing thing that I did not use this knowledge, that the current in that branch, is equal to IO. How can I relate the current of this branch to I4? It's really easy. I will pick a node. Let's say this is node PQ. Let's node S, and I will do KCL around S. So fifth, do KCL around node S. So doing KCL around node S, I will have IO is flow in, and also I4 is also flow in. So IO plus I4 is equal to 0. So this gives us IO is equal to negative I4. So this is equation 5. So I have 5 equations in 5 unknowns. So I will try to, in order to solve it using your calculator, so you have to, for example, substitute with equation 5 into the 4 different equations, and also reduce like I3 or so, in order to find to reduce it this equation to 3 equations. So I think you will be able to find it, and the final answer is I1 is equal to negative 7.8, I2 is negative 2.5 ampere, I3 is equal to 3.93 amperes, and I4 is equal to 2.43 amperes, which is give us IO is equal to negative 2.143 amperes, and this is the final answer. Thank you so much for watching, and see you in tutorial 5 part 2, which is related to 7 equivalent. Thank you so much. Have a good day.